Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting paper, our emerging abilities of large language models, or Mirage, right? And this is one of the best papers at NeurIPS 2023. Okay, so let's get started. What is emergent abilities of large language models? So, long back, there was this interesting paper from a Nobel Prize-winning physicist, P.W. Anderson. The paper is titled "More is Different in Science." And the paper basically said a very interesting thing. As the complexity of a system increases, a scientific system, right, new properties may materialize that cannot be predicted even from a precise quantitative understanding of the system's microscopic details, right? And at this point, he basically coined this term emergence. This particular property, he basically called it emergence. Recently, in large language models, people have observed emergent abilities. What does that mean? That basically means that if you look at small scale of these large language models, you do not find that they can actually solve some tasks. But on large scale models, essentially, somehow they cannot, somehow they are able to sort of come up with very good performance on these complicated tasks where small scale models seem to be either performing absolutely zero on in terms of accuracy or very, very minimal performance. Okay. There are examples where various large language models like Lambda, GPT-3, Gopher, Chinchilla, Palm, they have basically shown a significant increase in performance, in accuracy across many, many tasks. So you see these 8 different tasks here, word unscramble, Persian question answering, truthful QA, grounded mappings, and so on, 8 different tasks. And all of these models, on the x-axis, what you see is increase in the model size. And what you observe is that suddenly at some point, suddenly the model becomes capable of solving these tasks. Like suddenly you start observing way more than random accuracy. The red lines are random accuracy, right? So until that point, smaller models are essentially almost like random, but suddenly there is a point where the large models become super awesome and they actually start showing ability to be able to solve these tasks. Okay. So there are two interesting defining properties of these emergent abilities in large language models. One, sharpness. So there's a sharp transition seemingly instantaneously from not present for small scale models to suddenly possible and present for the large scale models. And second, unpredictability. So transitioning seemingly transitioning happens seemingly at unforeseeable model scales. You don't know at what model scale it will happen, but suddenly just happens at some model scale. Okay, so there's unpredictability about when the performance will improve, and it improves suddenly sharply. Okay. So in this paper, they basically try to debunk this in some form. Well, I mean, debunk is probably a strong word, but they try to analyze it and try to sort of broadly conclude that these emergent abilities in LLMs are more like a mirage. Okay. In fact, they basically mentioned that these emergent abilities in LLMs happen because of two reasons. One, because of the choice of the metric that the researcher makes. So the nonlinear or discontinuous metrics lead to such a mirage. And second, too few test data points to accurately estimate the performance of smaller models. So for smaller models, you basically show that there is very low accuracy because you just experimented with very few test data points. Okay. So here is a picture showing 6 different plots. So the first plot basically just shows that, yes, the training is perfect. Per token, if you basically are talking about generative models, per token cross entropy loss seems to be decreasing monotonically with model scale. So as the model scale increases, yeah, per token model loss sort of decreases, entropy loss decreases, right? And accordingly, if you basically compute the probability of the single token, which is like e raised to minus the loss, essentially, and you try to compute it with respect to the increase in model parameters, it sort of increases very smoothly. So it sort of increases smoothly and continuously in that senses. Okay. And it has asymptotes to 1. So in the sense that if you have an even larger model, it will basically reach close to 1 in that senses. However, if you have metrics which basically are with respect to multiple token predictions, for example, accuracy of an answer which is generated by a generative model, right? You start seeing nonlinear. The metric actually scales nonlinearly with nonlinearly scales the performance, okay, causing emergence. So, for example, as you observe here, suddenly at a very large model scale, there is a very large jump in accuracy. Okay. Similarly, so this is basically because you have accuracy as a metric which is nonlinear in nature with respect to multiple token predictions. Because if you're generating multiple tokens and evaluating accuracy, exact match accuracy, for example, it's sort of nonlinear in that senses. So such kind of emergence can also be observed if you're basically using a discontinuous metric, for example, multiple choice grade. So if you have like 10 classes and you're trying to basically figure out which of those classes are relevant, it's more like it's more like a step function. So basically what you observe is discontinuous metric also scales performance in a sharp manner. In that sense, it's causing emergence. Okay. On the other hand, if you replace these metrics, replace accuracy with, let's say, sort of number of incorrect tokens, also called as the token edit distance, then what you would observe is that you would not observe any emergence. There's a smooth and a continuous transition in that senses. Similarly, if you replace this multiple choice grade with something called as a Brier score, which is a more of a continuous metric, you'll basically observe that, again, you do not see any emergence, but you actually see smooth, continuous, and predictable improvements in task performance. Okay. So they actually did this analysis using GPT-3. So GPT-3 is emergent, so-called emergent arithmetic abilities. Okay. So what you see here are, of course, 3 rows, 3 columns. On the 3 columns, you have 3 different tasks. So this is mathematical modeling task. This is two-digit, two-integer multiplication task. This is two-integer, four-digit addition task. Okay. So that's that. The 3 different tasks, 3 different columns. Okay. So what you observe is that on the top row, you essentially see accuracy is being plotted. And accuracy, as I just talked about, is basically a non-linear metric. And you see emergent capabilities, right? Suddenly, this large model effectively has super awesome accuracies for all the 3 tasks, while the smaller models somehow do not have very good accuracies. Okay. But what you see in the middle is basically replacement of accuracy as a metric with the token at distance. And as you observe, this is basically predictable, smooth, and relatively smooth, and a continuous kind of movement. Of course, there are some discontinuities here as well, but then relatively, it is much more smoother and much more predictable in that senses. Okay. And further, in general, if you basically just compute accuracy, you probably don't even need to compute exactly token distance, but you compute accuracy. But this testing is done on much more larger test data. So, augmented test data, additional test data is added. Then again, you'll observe much more smoother, continuous, and a predictable increase in task performance with respect to model parameters. Okay. Now, they did yet another interesting experiment where they basically said that, okay, in convolution, in vision tasks, people have typically not observed emergent abilities. So let's try to bring in some emergent abilities. How about that, right? By changing some matrix. So that's what they did. They basically took a CFAR data set and tried to learn nonlinear autoencoders on it. It's just that rather than computing the accuracy of those autoencoders using the standard mean squared error, they actually came up with an interesting reconstruction metric where the mean squared error, where you would define the mean squared error as an indicator function over the error, the actual error being less than C. Okay. So it's a as you see, there's a non-linear-ish kind of metric where the MSE is bounded by C. If it is less than C, then you'll call it 1, else you'll call it 0. Okay. And what you observe is that if you, so this is an example of what emergence means, right? It has to do nothing with this task, but it just shows what emergence means. And this is the plot that you obtain if you actually do MSE as a metric, which is linear, which is basically a good linear and continuous metric. And the plot also looks very reasonable. As you scale the number of parameters, of course, MSE should drop. So that's good. Okay. However, what you observe here is that this reconstruction kind of a metric that is defined as a nonlinear metric, you suddenly see emergence here just because essentially, just because this metric is nonlinear in nature. So this is how you can actually induce emergence in vision tasks also. Here is another example, emergent classification of some omniglot characters by autoregressive transformers. Here it is a classification over a sequence of characters. And as you observe, so this is basically a plot of some unrelated emergent ability using some model, GPT-3 model, right? And as you observe, if you were just using typical accuracy, you would, so accuracy basically means that, even if you predicted a few of those images in the sequence correctly, you would still consider it as accurate. But here is basically a plot which basically says that this is using subset accuracy. And the subset accuracy basically means you are going to consider it as 1 only if all L images were correctly classified. Okay. So what you observe is that this typical accuracy, which basically just measures, even if anything in the sequence is correct, you would typically give partial accuracy in that sense. Is it's much more smoother a metric, and therefore it's much more smoother curve here of variation in the accuracy with respect to the size of the model. But as you observe, there is an emergence kind of thing that happens here when you change the metric to subset accuracy in that sense. So basically saying, yes, if you change the metric, you can actually induce emergent abilities, even in networks where people have never seen or reported emergence abilities in the vision tasks. Okay. So in summary, in this paper, an interesting thing that is concluded is that emergence in large language models is a mirage. Okay, so we need not be sort of worried about you train a very large model and will it sort of come up with an ability to take over the world. So something of that kind hopefully will not happen, right? GPT-3's emergent arithmetic abilities vanish when the metric is changed or when the test dataset size is increased. And third, just to prove their point, they actually try to induce emergent abilities in networks for vision tasks and successfully are able to do so, thereby showing that emergent abilities are really a reflection of the researcher's choice of the metric or the test data set that they have used to report those results. Okay, so hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage.